So, today we'll try to do two things. We'll finish the proof, we'll start and finish the proof that 3-sum is not SATH hard. And then we'll move to completely opposite direction and prove that edge coloring is not SATH hard. So this is our two main goals. So there will be two different techniques. We'll try to cover both. It will be lightning fast and hopefully really fun. Okay. Any questions from the last time? I'll try to recap really briefly what was happening, but any burning questions right now? Okay. Let's start then. So, in the first section we will talk about NSATH. Let me talk a little bit about it. NSATH is non-deterministic strong exponential time hypothesis. So where this hypothesis is coming from? Well, like some time ago we started this quest on reducing number of conjectures. Like we're trying to prove that 3-sum is SATH hard. So we can we don't need 3-sum as a hardness assumption anymore. Or like all pairs of pass is a SATH hard problem. Or set cover conjecture is implied by strong SATH. Well, we end up having one more hypothesis. That's all we end up with. We just introduced one more hypothesis and that's it. Okay. So let me remind you what we finished on last time. We have this general strategy of how to prove that something is not SATH hard. So this is like a natural strategy, right? We find some property such that all SATH hard problems have this property. And then we prove that some problem doesn't have this property. Okay? And then this is the property we will be using. Let's take a close look. So in coarsely grained complexity, we had that it's in NP intersect co-NP. And here we have a fine-grained analog of that. We have that for the problem, we have a fast non-deterministic and faster than, we have a non-deterministic algorithm that's faster than deterministic, and co-deterministic algorithm that is faster than deterministic. So we have unexpectedly fast both non-deterministic and co-non-deterministic algorithms. And this is peculiar situation. And we mentioned that that all the problems that are SATH hard have this property. Yes, and 3-sum doesn't. Okay. Let me just. There was some confusion from the last time about what I actually mean when I say non-deterministic and co-non-deterministic algorithm. There are all the definitions are equivalent, but to better understand what I'm saying, let me just say what I have in mind when I'm saying those words. So, by non-deterministic algorithm, I mean that there is a proof that can be algorithmically checked in some time f. Okay?
Proof of what?
Proof that given instance belongs to the language. So we have some language L, and if it has non-deterministic time complexity f, if for every instance of this language we can prove that it belongs to the language and verify this proof in time f. Okay? And by co-non-deterministic algorithm, I mean that there is a proof that instance doesn't belong to the language. So I think of both as existential proofs, right? So one is proving that it does belong, and the other proves that it does not belong. Okay? Are we good on this? Okay. Questions? Okay. So every problem. So again, for all the when I'm talking about fine-grained complexity problems, we're talking about a pair of a language and some time complexity function. Otherwise, it doesn't make sense. And when we're talking about reductions, we're talking about reductions between a pair, language complexity to language complexity. So our main theorem today is that all SATH problems have this property X. But we can prove that. Well, so this is the problem. Yes?
The X is the property defined by the first line, isn't it?
Yes. Yes. Yeah, it's just like really long line. I don't want to use it too many times. So the problem is the same as with Kearsley-Lagrange complexity, right? There we had that all problems to which we can reduce 3 SAT are not in NP intersect coNP unless NP equals to coNP, right? So we need some fine-grained analog of this assumption. We need to condition it on something, because like proving something like that would be totally out of our current range of technology. Like proving this result would be like incredible. You would be the most famous person ever. So let me introduce you one more hypothesis that we will be using to prove irreducibility results, right? So it's non-deterministic strong exponential time hypothesis. It's a non-deterministic analog of strong exponential time hypothesis, which the name suggests. Okay? So there is no co-non-deterministic algorithm that solves k-SAT faster than 2 to the 1 minus epsilon to the n.
1.
Sorry?
Sorry, its complexity is really 1.
It should be n. I'm sorry. It should be. So you cannot beat the brute force even with given non-deterministic bits.
Why is called n-set but not co-n-set?
Because there are too many letters in co and set. Yes. Okay. Any questions about this hypothesis? Okay. So it's just plainly the same thing, but we now allow algorithms to use non-deterministic bits to prove that that formula is unsatisfiable. So should you believe in SSH? Well, I find that like roughly all the same reasons that you can use to try to convince yourself that you should believe SSH, they basically applies to NSSH. So first of all, people try to refute this problem. Like the whole area of like proof complexity try to do something like that. We have people try to develop algorithms. They failed. So yeah, we tried, we failed. We believe it's hard to do. Right. So the other reason that is nice is that if you refute NSSH, you will prove circuit lower bounds. In particular, you will prove something like that e to the np, with oracle in np is not computable. Yes, that is a good idea. So if not NSSH, then e to the np is not a subset of linear size TC0. And if you know what that means, you know that it's pretty pathetic. But on the other hand, we are incredibly far from proving anything like that. And actually, this is a result from this year by Amir, who didn't made it here. But yeah, this is pretty cool.
Was it about NSSH?
I mean, it's about SSH. They stated it's about SSH, but you can convert this result to NSSH by saying like 2 more words.
Is it always like
Yes, yes. If you prove some circuit lower bound under SSH, it's almost automatically is proven under NSSH. So it's not an argument why. So first of all, we believe that this statement is true, right? So it's not an argument that NSSH is correct. It's an argument that it would be super hard to refute it. Which means that it makes sense to write papers under this conjecture. They will not be disproven in the next few years, right? So, I know. Okay. Yeah. So.
So could you tell again?
Yes.
NCTH states that
There is no core non-deterministic algorithm that solves SAT faster than 2 to the n. It's the same definition as SATH, but with word co-deterministic stuck wherever you wanted to put. Yes?
What the situation is similar to the SAT, where for 3 SAT, for example, you have faster algorithm, for 4 SAT, and
Yes.
goes to the end, also for the end.
Yeah, we have absolutely the same situation. We have actually, the problem is we don't have better co-non-deterministic algorithms than just deterministic. No one managed to use non-determinism in any way, as far as I know. So the currently best co-deterministic algorithms are just deterministic algorithms. So yeah.
I don't understand something of this. So, what is the fastest non-deterministic algorithm for SAT?
Non-deterministic,
Yes.
it's like linear, right?
Right.
Yes.
But
But non-deterministic, so you're trying to prove that formula is unsatisfiable.
okay.
And well, so the idea that like we don't know any useful proofs. So if you'll be stuck in a room and like you'll be super smart and I'll have a formula that I want to prove that it's unsatisfiable, we don't know any way you can help me.
In linear time.
No, not even in linear. We don't know any way he can help me at all. Right? That is a problem, right? So like we even we have like with access to mastermind that which we don't trust, we don't know how to use. There is a better algorithm if you have access to Merlin. So if you have proof that you're allowed to verify with access to random bits, then you can do better. But yeah, for deterministic versions, we don't know anything.
So anything you're going to show will rule out only deterministic reductions.
Sorry?
Anything you're going to show us will rule out only deterministic.
Yes, it will only rule out in deterministic reductions. Yes, that is correct.
So
And what is more difficult, counting assignments, or I guess how many assignments are there, or solving scores on deterministic?
So yeah, I think counting should be harder, right? It's probably, yeah. So yes, so these all SATH hard problems have this property X under NSATH, and that's how we will use this conjecture. All right. So in this proof outline, we're using NSATH as analog of NP not equal to co-NP in Kersley-Grain complexity. All right. Right. All good here? No. So we proved that.
I just want to go back again.
Yes.
So assume that I would like to break NSATH.
Yes.
Would it be enough to construct a proof system that can prove any satisfiable?
Assignment faster than to do then. Yes. Yes, and
So
we.
we don't even need to do this like algorithmically. We just need.
So yes. So proof systems are usually that you should be able to verify them easily, right? Yes. So if this is true, then yes. But we can ask for a proof, and then just we need to verify it faster than to do that.
So is it true that, but in proof complexity, they are trying for various proof systems?
Yes. So they actually have. Usually it's not NSTH. There is other hypothesis called NETH, right? Non-deterministic exponential time hypothesis. And NETH was proven for different proof systems, right? So if if our algorithms are not just any algorithm, but algorithms from a particular family, then we can prove that they have to like span exponential time. I don't know of any results of NSCH form for proof systems actually, which is kind of funny.
Like even for resolution?
Even I think even for events, I mean, I don't think anyone ever bothered. So yeah, so the idea that like
But you just like 5 minutes ago you told us that like despite of intensive research.
yes, no, but not okay, not in proof in proof complexity they really try to disprove an ETH, but yeah.
So I think NSCH, so it's naive and spread. So they try to prove that.
Yes, I know that they tried. I haven't heard if they succeed.
Yeah.
Yeah.
Nobody bothered.
Okay. Yes. Okay. No one. Back in the days, no one bothered, and yeah, and now there are a few people who are trying. At least were trying at some point. Okay. Let's get back to. Let me remind you what is fine-grained reduction. Right, so again, we have a reduction from a problem and complexity to a problem and complexity, and reduction should be fast, and sizes for the oracle calls should be of right proportion, right? Okay. Again, we'll try to do the same trick as before. It would be just the same thing, right? So suppose we are given a reduction. We will convert this reduction to a non-deterministic algorithm. That would be better. As if we have a problem that doesn't have X, that is SATH hard, we will provide a faster non-deterministic algorithm for SAT, which will rule out NSATH. So suppose we are given this reduction, and this is like schematic description that like red circles are when our oracle is telling us that this instance is not in the language B, and blue circles is that when oracle is telling us that it's outside of the language B. Yes? Oh, it's just that it's a symbol that we're using reduction as a black box, more or less. Yes. Yes, it's a running process. Yes, and then it's just making calls. So this is a reduction from A to B, from some function F to some function G, and suppose we know that B is in this, has both fast non-deterministic algorithm and fast co-non-deterministic algorithm. That should imply that A also have a fast non-deterministic algorithm and fast co-non-deterministic algorithm. Right? Well, why? Again, we are using this to construct, let's first construct non-deterministic algorithm. We just running the reduction. Whenever we are making oracle call, we ask our non-deterministic bits to tell us the answer for the oracle first, and then run either non-deterministic or co-non-deterministic algorithm, right? They're both running faster than faster than G, which means that in total they would be running significantly faster than F, which means that we just constructed a faster non-deterministic algorithm. And absolutely the same for co-non-deterministic thing. So that's just reduction. We're just using reduction and provided algorithms instead of oracle calls. Nothing can be there. Any questions about this? It's absolutely the same as we did before, instead of like just fine-grained version of the proof we used yesterday.
So we impose such a property on B that it could be solved by NP oracle and by co-NP oracle.
Yes.
There are not so many functions like that.
Well, we will show a few. Okay.
So could you please repeat
Oh, because so some of our oracles or some of our calls to the oracle are for instances that belong to the language, and some are that not belong to the language, right?
Okay.
So when they belong to the language, we need to prove that, and we have to use non-deterministic algorithm for that. But if they don't belong, we still have to prove that, and we will use co-non-deterministic algorithm for that. So we need existence of both.
So by this, you mean that the oracle returns either the proof that this instance belongs to?
Yes, or the proof that it doesn't. And because it's in this class, we know that both proofs are pretty short.
Right, and so when you make a call, before making a call,
Yes, before making a call, you ask your own non-deterministic bits to tell you the answer ahead of time.
you first ask,
Yes.
then you ask the corresponding.
Yes, and if
And then you verify it.
yes, and if the proof is not correct, you just reject the whole thing, right? Because your non-deterministic bits were wrong. And at this point, you can just say, "I give up. I can't work in this condition, so I quit."
Right. Could you just ask both oracles and then verify one of them?
Yes, you can do that. You can do that instead. Yes, you can ask both non-deterministic and co-deterministic algorithm and check that one of them is correct. Yes. Yeah, it's a different way to put the same, to do the same.
So which basically means that you do everything deterministically or not?
No. To simulate non-deterministic and co-deterministic algorithms, I'm using non-deterministic bits.
Oh, I see.
Right? I need it inside.
All right.
Okay. Are we good here? Any questions?
Sorry, so we just noticed that we actually don't need this random list to choose which oracle to
Sorry?
We just, I'm not sure if I understood you correctly. So you said that we don't need to use this random bits to decide which oracle.
Oh, so we can just run both of them if we want, yes. But we will still need non-deterministic bits inside the simulations. All right. So now we'll actually prove that threesome has both fast non-deterministic and fast co-non-deterministic algorithm, which would imply that it doesn't have X, which would imply that it's not an SATH hard under an SATH. All right? That's a general idea of what we're going to do now. How much time do I have?
Just half an hour.
Fantastic. Okay. So we have this problem. I know you've seen it already, but yeah, we given n numbers from some range from -m to m, and we think of m as being like polynomial in n. And the question is, are there three numbers that sum up to 0? All right? So we have two very famous algorithms. We have algorithm that runs in, so the obvious algorithm run in n cube, right? Just check all the triples. If you try to be smart, well, you can compute all the sums of the first, all the sums, all the pairs of the array. It would be n square of those, and then you sort them, and you solve, and then you look for, let me just write. Okay. So you have an array, you compute all the ai plus aj, right? You sort it, and then for each element, you just verify that the opposite is in this long array.
Sorting requires a bit longer than
Yes, so you will solve it in n square log n, right? This way. Then it's a really good exercise to solve it in n square by like ditching the log factor, and then with a lot of pain you can shave one more log or even log and a bit. But like by having, so but still the best known algorithm is roughly n square over log n. Okay, and the conjecture is that you cannot shave a lot more. You cannot have like n to the 1.99 algorithm, right? This is the conjecture. And what is the non-deterministic algorithm for that? Yes, exactly. You just get three numbers, you sum of them, they're either 0 or non-zero. You're done. So what is the time complexity of that? It's actually n, because you still need to read the whole input. Yes, exactly. Yeah.
So you skip this big O of M.
Oh, yes, thank you so much. Yes, so we will actually need it a lot. So there is another algorithm that solves this problem in O of M. And I had a brief look at what you've been doing with Pavel and. Oh? No, it's a fast Fourier transform algorithm. So what you can try how you can do it, you just write down the following polynomial, x to the a first plus x to the a2 plus x to the a3 and so on. And then take a cubic power of it. And then you check the coefficients in front of the constant. So the idea is that if I know the value of the coefficient in front of x to the 0, it is exact. Sorry? Say again?
Some negative powers. So it's not quite.
Yeah, well, that's not. Yeah, plus something. Yeah, plus m. It's a good suggestion. Yes.
So without that, it will be
Yes.
n log n. If there was no m, then it would be.
It's still m log m. Yes. This tilde symbol means that I'm hiding some log factors, and I will not be concerned about them at all. But yeah, so in this thing, so we are looking for the coefficients in front of a to the x to the 3m, right? And yeah, we can compute this coefficient in our family using fast Fourier transform. All right? Okay. So the whole idea, the whole problem is to actually came up with a non-deterministic algorithm, right? And this is what we'll be doing. What is the idea behind those like non-deterministic algorithms that we'll be talking about is the first you try to embed your problem into a simpler problem. Right? But this embedding will if it would be just a reduction, then your problem is easy. But by embedding, I mean that you will have some number of false positives after this transformation. And then what we'll do, we'll try to guess all those false positives. We'll guess them. We'll check that they're actually false positives rather than just positives. Then we'll count the number of. So this is where we're using non-deterministic bits. Then we just deterministically count the number of false positives on our own to verify that the given to us list is complete. And then we are done. Okay. Questions? This is super vague, but still. It would be a lot easier to follow with a concrete example. Okay, so what do I mean by embed in terms of threesome? Well, we'll just take the whole problem modulo some prime. Right? Okay. Then I'll ask for all the. I use my proof is all the triples that sum up to 0 modulo this prime. All right? And for each of them, I have to verify that They sum up to 0 modulo this prime. And well, they are not the solution to original instance. Otherwise, it's not. So we are trying to come up with a proof that there are no triples that sum up to 0. If you just found one, well, you're done. So, okay.
So once again, you guessed both P and T?
Yes. Yes, I guess both P and T. I will have some constraint on them, yes. But.
How will we check that all other triples do not sum?
Yes, and that's where the third part comes into play. We'll count number of solutions modulo this prime, and if the number that we get is equal to T, well, then the list that was given on the previous step is complete, right? And then it's a proof that there is no solution, because every actual solution of 3-sum would be a solution modulo P. All right? Okay. So by non-deterministically, I mean that we are asking a proof that there are no triples that sum up to 0. All right. Any guesses what?
So once again, at the second step, you count
So
solutions modulo P, which are not real solutions.
in this?
Yes.
In this, I just verifying my list that is given. So a prover is giving me a list of numbers, and I verifying that each of them is a solution modulo P and not a solution of the original instance. So.
You still check that there are no others triples that sum up to 0 modulo
Yes.
P. And this proves that there are no triple 0 triples.
Yes. So before we'll go into the details, because like we need to figure out why that actually works, right? But so any question? Yes. Yes.
At the third step, if you reject it actually in two cases. The first one is if the number of solutions modulo P is different, but there is also a case when.
So if on the I reject in two cases. Either some triple on the list doesn't satisfy one of those two equalities,
Right.
or on the third step I am not getting T. Right? I cannot get anything less than T because I already know that there are at least T solutions. But I can get more than T, and that means that prover is cheating, and I don't trust him, and I quit. Okay. So, any ideas? How large should I pick P? So now the question. So okay, first of all, how long does the first step works? How? Oh?
Depends on the size of
P would be like something small, some small polynomial. Yeah, so the first step is super simple. It's just linear. You just take all the numbers modulo P, right? Well, you don't even do that. You're just picking P, which is like logarithmic number of bits, right? Okay. Oh? Oh, constant. Depends on your model. Okay. So how long does second step takes? T. Exactly. So how long third step takes? Sorry? Yes, this is exactly where we can use fast Fourier transform algorithm. So there are two ways you can do it. You can use polynomials over the field Fp and just use fast Fourier transform over there, or you can do this. So suppose A prime, AI prime is just A mod P. Okay? Then what I'm looking for here, and instead of M, I will have plus P.
You don't need plus P anymore.
Oh, I don't need, they're all positive. That's fantastic. Yes. That is fantastic. Okay, so which coefficients now I have to check? Oh? Yes, yes. So I need to check coefficients in front of x to the 0, x to the p, and x to the 2p. I don't need to check x to the 3p because it's impossible to have it, right? Because the degree of this whole thing is at most 3p minus 3. All right? So we can do this in order of m, in order of p times some log p. All right. So we can do the second step in t and the third step in p. So the question is, how small can I make both of them simultaneously?
P and T?
Yes. So I want to prove that there are always like small p and small t, such that this whole proof is correct.
And the intuition is that the smaller p, the larger is.
Yes. So yeah. If you take a really small p, then you will have a lot of false positives, right? So let's try to think about that. How can I do that?
But it depends on also on how many zeros you be that so that
Yeah, we need this proof only to exist when there are no real solutions for the instance, right?
no triple is 0.
Yes, no triple is 0.
If you take random p prime, then
Yes.
there are just few of them that could divide the sum of the string.
Exactly. That is exactly the intuition. So we have n cube possible triples, right? And they are all non-zero. If I pick a random prime, p is from between 1 and p0. Actually, let p be the first it can be prime intersect first k primes. What are the chances that a concrete triple is divided by this p? Something like that, right? So every triple sum up to some polynomial number. Polynomial number can have up to order log n prime factors. Log m prime factors. But m is a polynomial, yeah. Right? Are you on board here? Which means that we have probability. So ai plus aj.
So do you, at this point, do you assume by default that there is no triple?
That sum up to 0. Yes. Yes.
In this case, we just reject immediately.
Yes. So we mod p equals to 0 with probability order of log n over k. Right?
K is used 2 times.
K is O. All right? Sorry? So this triple is some concrete number, right? Of order 3m, which means it has about at most order of log m prime factors, and yeah.
You assume that capital M
is polynomial in n. That was part of the definition. Yes.
That's a problem.
Yes. So.
Numbers are polynomial.
In n.
Is it given us? Or
Yes. Yeah. We assuming that. Yes. Sorry?
Do we need to care how the sum of the triple is distributed?
No. Right now we are talking only about like one concrete triple. So for every concrete triple, we have this probability, right? Which means that on average, number of triples equals to 0 mod p is something like n cube order of log n. It's up to log factors n cube over r.
So this is a problem because you have the last step n log n time.
Yes, exactly. So I will pick r to be roughly n to the 3/2. R would be n to the 3/2, which means that I would have, on average, I would have t, if I pick a random prime between 1 and n to the 3/2, I will have about t about n to the 3/2, right? And if it's true on average, then definitely I can pick one for which is true. Well, not me, but I will ask my prover to give me such a prime. So we can make, and there are, so, like the first n to the 3/2 primes are in the span of the first n to the 3/2 time log n times some constant numbers. So up to log factors, it's all the same. So yeah, we can make p and t simultaneously about n to the 3/2.
What is R?
R is,
What value of R?
so R would be n to the 3/2. All right.
But it could be anything up to n over 2.
Yes. If let's give you the optimal running time for this algorithm. But yeah, you can. If you don't care about that, if you just want to make it below n square, then yes.
And third step is running R log R.
Yes. Yeah. Yes.
When we say that we choose something random, we actually mean that the algorithm will check all the possible cases.
So no. When I'm saying that so we'll not pick a random prime. We used the random argument to prove that such prime exists, right? And then we'll ask the prover to give it to us. So because we don't have access to random bits, we have to rely on non-determinism as a good substitution.
I mean, you don't need any probability key. You can just write inequalities here. Right?
Yeah, so you just need existence. Yes, you don't need it's.
I mean, you just what you're claiming here is that this sum of three elements cannot have too many.
Yes. Yes, and then there exists a prime which is not a prime factor of too many triples. Yes. All right. And so we have this. We have a linear time algorithm that is non-deterministic and n to the 3/2 algorithm that is co-deterministic, which implies that 3-sum is not SSH hard unless n SSH fails. So, yeah, so again, it just means that this reduction is implausible. It should be super hard to come up with. It should require some fascinating new ideas. So if you give me a reduction that just like, is simple, I will just reject it because people definitely tried all the simple things. Right? So all the people who work in circuit complexity, all the people who works in proof complexity, all the people who works on SAT algorithms, it means that you should came up with something that they all missed. So it should be something like really hardcore. All right? Yes?
So right now there are two options. What do you think is more probable? There is a faster non-deterministic algorithm at 3-sum, or that there is a reduction from SPH to 3-sum, but not tight. So only rule out.
Oh, this is a fantastic question. So the question is there like a reduction that, for example, goes to that proves n to the 3 halves for 3-sum under SSH, and so we ruled out every reduction that proves. So we ruled out not just 3-sum n square. We ruled out 3-sum n to the 3 halves plus alpha for all alphas more than 0. So for all alpha more than 0, this is not SSH hard.
So just to clarify, if alpha is a small constant, then this statement is actually stronger than
Yes. So we cannot, we can't even prove n to the 1.6, but to rule out n to the 1.5, that would be really nice, because that seems to be super related to proving SSH hardness of subset sum. Not the pseudo-phenomenon, 2 to the n over 2, yes, 2 to the n, right? Because you can reduce, if you had 3-sum algorithm that is faster than n to the 3 halves, then you can solve subset sum faster than 2 to the n over 2. So there is no formal connection, but I feel like those two questions are related, and so that makes it super interesting, actually. Yes?
Could you again show the definition of X? So X is
Okay, how much time do I have?
5 to 10 minutes.
Okay. So let me just try to scratch the top of the next topic. So this is a cool thing because we will prove irreducibility kind of unconditionally. So the statement would be, if there is such some reduction, that is just ridiculous. That's almost a correct statement of the theorem. Okay, so one very important thing you should know about fine-grained complexity is that all our reductions are going down. We start with a hard problem and we reduce them to simple problems.
There is the exception of the previous lecture that goes up, but only slightly.
We can talk about, we'll talk about it in a second. Actually, the answer to your question is no, it does not. The thing is that the letter n is horribly misleading, and it goes down in terms of the size of the number. Like if we talk about number of bits you need to describe the instance, then even those reductions are actually going down. Right? So there are some good examples. We know the last exactly. We know how to reduce 3-sum and square to 0-weight triangle and cube. Where is the catch? Yes, the size of the input to 0-weight triangle is actually require n square bits to describe it. So n when we talk, so yes, that is the whole point. That when we talk about problems on arrays, n is the number of elements of the array. When we're talking about formulas, n is the number of variables. If we're talking about graphs, n is the size of the graph in number of nodes, right? And all those numbers are it's just like in some natural parameters. But when we go to unifying parameter, which is just size of the instance in terms of bits, you need to describe, or numbers you need to describe it. Then you need n square bits to describe a graph, right? You need to write the adjacency matrix. which means that zero-way triangle is actually S to the 1.5 hard problem, which means that it's exactly this reduction is reduction down. All right? So, and the good question is like, why, right? So there are two amazing results you can try to prove. You can try to find some upwards reduction. Just can you reduce orthogonal vectors to CNF SAT in a fine-grained way? Can you reduce 3-click to 9-click and so on? Or can you find some explanation of why we don't have those reductions? So, okay, there are reductions that go up. The problem is they're just silly and ridiculous. Those, for example, you can reduce orthogonal vectors to some padded version of orthogonal vectors. Just add enormous amount of like zero vectors. So you know, like, or just add something, some rubbish to the input. The problem will get easier in terms of the size of the input, but this is not the answer we are looking for, right? So, okay, and one of the natural questions about upwards reductions is edge coloring problem. So edge color problem is a classical graph problem. We give a graph, and we want to know if you can color every edge in some number of colors, right? Such that no two adjacent edges are colored in the same color. And the best known algorithm runs into 2 to the m, which is for dense graphs around 2 to the n square, right? And the question is there a better algorithm? So, and if not, maybe we can find some proof that, for example, ETH hard to find a better algorithm. And there was a very recent result about that. The least version of this problem is actually ETH hard. This is a very fresh result by Marek and co.
What is the size of the list? What is the size of the list?
Up to n. Yes. So this is a, oh. Yes. In the reduction up to n. Yes. Full blown. Yes. Yeah. So and this is kind of a problem in terms of that while this is syntactically very, very close, this is still a downwards reduction because size of the input. So let's see what's the problem. The size of the input of edge coloring is n squared, which means that we are looking to prove a lower bound of form 2 to the s. And what about complexity of SAT? So in fact, SAT, it requires 2 to the n, and size of the formula is around n log n after specification, which means that complexity of SAT is 2 to the s over log s, which means that if we prove an ETH hardness of edge coloring, it would be an upwards reduction, which would be amazing. But when we're adding lists, we're blowing size of the input from n squared to n cubed, and now it's a downwards reduction. So while syntactically it's super close, I feel like there is a universe of difference. You cannot. I don't believe that you can use the same proof technique to prove the same. So you cannot use the technique from this result to prove that result. Yes.
You just said after the specification lemma on the side of the input in log n, right? Isn't it just O of n?
O of n clauses, yes. But to describe a clause, you need log n bits, right? So the whole formula is described by about n log n bits. Yes?
But to encode each card, we need n square bits or n square log n bits?
In the dense case, we need n square, right? Because you can just have an adjacency matrix.
But also you need, for every h, you need to encode the name of the h, right?
No, but I just can describe a graph, right? I can just describe the whole. So our input is just a graph, and graph can be described in n square bits. Okay, there is no cheating here. So, yeah. So how much time do I have? Like none. Okay. So then just the statements of the problem. Okay, the first question is, can we prove that edge coloring is SATH hard? Well, we're not proving anything about ETH hardness of set coloring, edge coloring, but we can prove something about SATH hardness of edge coloring. So if you give me a fine-grained reduction from SAT to edge coloring that proves 2 to the Cn square lower bound, it disproves SATH. Which means that you cannot base hardness of edge coloring on SATH because this reduction will disprove SATH. Right? So there is no meaningful hardness result here. What? Yes?
What is published?
Sorry?
When was this published?
That was never published yet. This is a result by myself and Russell and Pagliazzo, and
It sounds like an unconditional result.
this is kind of an unconditional result. Yes. So there are. Yes, you can formulate this. Any reduction from so any result of the form edge coloring is SATH hard is ridiculous, right? Because it disproves SATH.
What will be then the result for edge coloring?
So we still cannot rule out ETH hardness. That would be nice, right? So it just means that we cannot pinpoint the constant from SATH, but the good open problem is to prove 2 to the omega of n square under ETH, and we don't know how to tackle this problem in any. Yes. So yes, I can. It's called no memorization. So the idea is that every time, well, we'll do some tricks, but the important idea, which is super simple, is that whenever we'll try to do the following. Whenever I'm trying to do an oracle call to the problem, I'll just do memorization. I'll just check if I've already solved this instance. And if I did, well, I'll just use that answer. And we will make sure that this memorization is useful by doing some stuff. And that's it. That would mean that we will use this reduction with this additional algorithmic trick to actually just disprove SATH without using like we used before. We used non-determinism, and here we don't need it. All right, I think it's a good place to stop. So next time we'll finish this. We'll show you how exactly this is done, and then we will move to coolest result I have under weirdest conjectures I have.
Stay tuned.
Yeah, so we will prove that there are no reductions whatsoever, no problems are SATH hard. I mean, like set cover, graph coloring, traveling salesman, you name it. Like all the problems are not SATH hard, and the conjectures you wouldn't believe.